Imagine traveling to the moon in less than 1 day, and to Mars in 3 months. Nuclear and fusion rocket technology could do that. Now, wouldn't it be more exciting to reach the moon in about 4 hours? And Mars in less than 3 days. And for those of you that are wondering if we are alone in this universe, Alpha Centauri can be visited and explored in 6 years. Hello everyone, Subject Zero here. 400 tons. 96% of the Falcon 9 mass is just fuel. 245,000 liters of liquid oxygen, 146,000 liters of RP-1 fuel. 5 terajoules is the energy released to travel 6 to 8 months and deliver only 4 tons of cargo to Mars with current technology. A payload with enough food and supplies to sustain a 4-crew mission for only 3 months. If we wish to get there faster and stay longer, we need to do better. How do we do that? Well, 5 terajoules of energy corresponds to 60 milligrams of antimatter. Not like we can find that in a local store. We could ramp up laboratory production, but that would still take millions of years. Is there any way to do this faster? How about capturing the payload for antimatter exploration and light nuclei astrophysics, also known as PAMELA. Kind of obvious why they used payload and astrophysics there. Had one simple mission: to verify the availability of antimatter at the Van Allen belts of Earth. Results as predicted for decades came out positive. The only question now is, how do we capture it? Penning traps, named after Franz Michael Penning, are devices that use electrostatic fields to confine clouds of positrons and antiprotons. The trouble is that these particles are charged, and charged particles repel. Because of that, there is a limit that Penning traps can contain until the cloud expansion becomes too great for the electrostatic repulsion to contain them. A simple solution would be to have several thousands of them. However, handling thousands of containers holding an extremely explosive substance only complicates things. Here is a better option. Trap and immediately process antimatter into antimolecular hydrogen. And that makes it easier because molecular hydrogen can be trapped by magnetic fields, if we manage to attain diamagnetic parahydrogen. Sounds confusing, but it isn't really. It's just that diamagnetic materials are repelled by magnetic fields, while the opposite, paramagnetic, is attracted. Diamagnetic parahydrogen is the most stable version of antimolecular hydrogen that can be trapped by magnetic fields. Remember, the last thing we want is for our fuel to be attracted to the magnets and go. With strong magnetic fields, the only thing left to do now is to cool down antimatter under 2 Kelvin in the form of snowballs. I'm not joking, that's how scientists call it, snowballs. Suggested solid core reactor technology follows the same principle as tested and proven nuclear core reactors. However, there are several differences in between the two, where the most obvious would be instead of uranium, antimatter is used to heat the propellant. The engine can be divided into 4 main parts: the magnetic confinement chamber where the antimatter is stored, the tungsten core where the reaction happens, propellant tank, and confinement shell leading to the nozzle. The core is made out of tungsten for several reasons: to protect the crew from radiation by absorbing most of the antimatter reaction products, both gamma rays and pions, to provide adequate hydrogen flow for cooling, and lastly, to delay the annihilation process. Like in conventional rockets, hydrogen is pumped into the cooled nozzle, making its way up towards the inside of the reactor. The tungsten core is designed to allow hydrogen flow and maximize heat transfer from the antimatter reaction, increasing outward pressure. The reaction heats up the hydrogen upwards of 3500 Kelvin, reaching specific impulse of 1000 to 1300 seconds. While the engine mass can reach 7 tons without the antimatter confinement, it consumes only 13 micrograms of antiprotons per second and 41 kilograms per second of hydrogen, generating 440,000 newtons of thrust. Now, instead of traveling 6 to 8 months to deliver only 4 tons of cargo, we can deliver 100 tons in 4 months. We can even further cut down the time it takes to travel to 2.5 months by using tungsten alloys, or any alloy that allows higher temperatures to be achieved. Take tantalum carbide for instance. Its melting temperature is above 4000 Kelvin. With this temperature, we can achieve specific impulses of upwards of 2000 seconds. All rocket engines suffer from the same problem: extreme temperatures. The true limiting factor here are the metals that comprise the structure. Though the temperature inside the reaction chamber can easily surpass 3000 Kelvin, the metal from the structure never reaches this temperature because they are being cooled by flowing hydrogen. The metal's melting point is at a delicate balance in between extreme heat and cooling that stops as soon as fuel ends, therefore keeping the engine intact. Technically, fission and fusion can all reach the same efficiency as antimatter. It's just that they fail in different ways. Back in the 1960s and 70s, the NERVA program produced and tested nuclear rockets. Its nuclear core heat provided the energy necessary to accelerate hydrogen out of the nozzle, generating thrust. This engine was so efficient that it reached 900 seconds of specific impulse and could burn fuel for over 100 minutes at 930 kilonewtons of thrust. The first problem is radioactive materials. Let's just say that the best engines needs uranium purity at levels of nuclear weapons territory.
FBI, open up!
Good luck convincing governments to allow you to make these. Not only that, but let's just say that nuclear chain reactions can go very wrong with poor maintenance. You could argue that small nuclear reactors in submarines have been working well for decades. True, but they are underwater. Let's just say that they have all the water they need in the case of an emergency. I'm pretty sure that they have proposed many ways of dealing with this in space, but it is a problem, a huge one, nevertheless. Well, on the other hand, fusion engines can do that easily. While it might take 30 additional years to develop technology from the point that they figure out fusion, which means forever plus 30, it can easily provide all the energy required to isolate everything magnetically. To reach reaction temperatures above 4000 Kelvin, everything that happens at the engine must be isolated. At the conversion nozzle, some estimates point to upwards of 16 Tesla. Just for a reference, the ITER toroidal field system produces a maximum of 11.8 Tesla with 41 gigajoule. Remarkably, in this case, energy is the least of any concerns. Forget about the reaction and the Teslas. For sure they're gonna make that work someday. Believe it or not, fusion gain isn't the problem here. It is the size and mass of the machine. I mean, just the toroidal field system that I mentioned earlier weighs 3,400 tons. I mean, what is the point of making an engine that can even propel itself? So far, we talked about technologies that are limited by material constraints, namely melting temperatures, endless requirements to sustain nuclear criticality, and engines that are heavier than the spaceship itself. Now, it's time to talk about the mother of all engines, the one that will finally take us to Alpha Centauri in 6 years, the one and only antimatter beam core. The antimatter beam core delivers an epic 10 million seconds of specific impulse. Delivering 23 tons or 6 times the payload of the Falcon 9 to Mars would only take 70 hours, with a benefit of 1G acceleration for 57 hours, 82% of the trip. The beam core engine is divided into propellant tank, solid anti-molecular hydrogen diamagnetic trap magnets, levitation lasers extraction system, magnetic feed and power conversion system, radiation shield, molecular hydrogen injector, and the magnetic nozzle. The extraction system uses lasers to guide the molecular anti-hydrogen snowball towards the feed system. The feed system magnets drive the snowball towards the magnetic nozzle, where normal molecular hydrogen is injected into the nozzle, encountering antimatter. The reaction releases 4.5 pions, 1.5 neutral, 3 charged, and a lot of energy. Charged pions can be directed by the magnetic fields, generating low thrust. To increase it, 100 grams per second are added to the mix, producing up to 10 million newtons of thrust. With 40 milligrams of antimatter, 500 kilograms of molecular hydrogen, and 23 tons of cargo, our spaceship could have accelerations of up to 30 Gs. Traveling to Mars would only take 54 hours, with a dead crew on arrival. However, keeping the crew alive with lower thrust, or 400,000 newtons, would benefit from a 1G acceleration through 95% of the trip. Sounds like science fiction? Yes, but most of the technology required to make this engine a reality already exists. But what about capturing antimatter? That's a huge challenge, right? Well, hear me out. With the first humans traveling to Mars this decade, the necessity for better and faster transport will increase exponentially. Unconventional technologies will suddenly be brought to the table, antimatter being one of them. At this point, it's not a question of how difficult it is to capture and process it, but more of how antimatter can improve space endeavors in terms of safety and financial feasibility. At the end of the day, every new venture is about that. Everything we need to get this done already exists. All we need now is just one less thing: your brilliant mind. Lord knows we need more people with the knowledge and skills to develop and construct these spaceships. If you think you are one of them and would like to dive deeper into these subjects, no pun intended, and sharpen your skills, then Brilliant is the place for you. By far, hands-on approach is the best way to learn something, and that is exactly what Brilliant provides. With tons of different courses for you to choose, from scientific thinking and essentials, all the way to astrophysics and special relativity. With interactive visuals, rather than just solving repetitive problems, they teach you the intuitive ideas behind topics like algebra, statistics, algorithms, and much more. Interactive learning helps you learn 6 times more effectively than watching lecture videos. So, if you did not understand anything I said in this video but found it fascinating, get started for free by clicking on the link below. Subject Zero, we're done here.